All right. Well, good morning, good afternoon, good evening, everybody. I am Jordan Gates. I'm responsible for product management here at Seabird Scientific. I'm here with Charlie Branham. We're going to talk to you a little bit about oxygen today. We'll have a short presentation, and then we have a video for to kind of walk you through the process. But with no further delay, I'll introduce Charlie Branham.
Thank you, Jordan. This is Charlie Branham, and I'm a principal chemist here at Seabird Scientific. My main primary focus here is new product development and technology advancement, and my primary focus is on pH sensors. And over the last couple of years, I've been working on the new oxygen sensor, the SPS 83. And Jordan's going to talk a little bit about some administrative things here before we get it started. So I'll hand it back over to Jordan.
Thanks, Charlie. All right. So like I said, we have a short presentation. We'll show a video after the presentation, and then we'll have about 25 to potentially 30 minutes to answer questions. But we do, for previous obligations, have to leave at 8:45. If you have any future questions after 8:45, please respond to the email. But with no longer delay, we'll get started.
All right, we'll talk today about why measuring ocean oxygen is important. We'll speak a little bit about the history of oxygen measurements in the ocean and where we are today. Then we'll lead into the design and performance of the new technology, the SPS 83 that we've developed at Seabird. And we'll close out with a factory tour of how we deliver sensors, oxygen and otherwise, through the design, the build, and the calibration process. All right, so person effects have contributed to a fourfold expansion of oxygen depletion in the ocean over the last 50 years, according to the Kiel Declaration on Ocean Deoxygenation. But why do we care? Nutrient pollution, ocean warming, ocean circulation all lead into a decline in ocean oxygen concentration. And you can imagine that a decline in ocean oxygen concentration leads into a reduction in primary productivity, a loss of ocean ecosystems, and a loss of biodiversity. So let's go back 100 years and to the Challenger expedition, where you can imagine maybe hundreds of ocean samples were taken over a 4-year expedition. And think about where we are today and how we got there. So in 1888, a few years after the Challenger expedition, the Winkler titration was developed, and that allowed us to accurately measure ocean oxygen concentration and oxygen concentration in the water, which we actually still use today to calibrate our instruments, or at least a form of the Winkler titration. In 1979, Seabird Electronics was established. We were primarily focused on physical oceanography parameters. But then in 1985, the Owens and Miller algorithm allowed us to develop an oxygen sensor and put it on a CTD. That oxygen sensor for us at Seabird was the SPS 43, which used polarographic oxygen concentration measurements. It's different than our primary oxygen sensor today, which is the SPS 63 and the SPS 83, which we now use on Argo floats. But in 2003, Seabird releases this first Seabird CTD with the SPS 43 oxygen concentration sensor for the Argo community. And then in 2007, the concept for a BGC Argo float array worldwide was established. From there in 2012, Seabird releases the SPS 63, and we've probably deployed hundreds of SPS 63s across the world, leading to thousands of oxygen measurements from the BGC Argo array across the world. So think over 100 years ago, hundreds of oxygen measurements in 4 years to thousands of oxygen measurements today.
What is BGC Argo? Well, it all started with the Argo program, which was established to monitor the physical state of the ocean over time, basically measuring temperature and the circulation of the ocean. Currently, there's a worldwide web of profiling floats. There's over just about 4,000 of them in the ocean right now, mostly outfitted with CTDs. Below is an example of a standard mission, Argo mission. Basically, the floats start at the surface, they go down to 1,000 meters, sit there for 10 days, and then they go down to 2,000 meters, and then profile up through the water column, taking measurements the whole time until they get to the surface, where they download their data via satellite for scientists to analyze. SeaBird played a critical role in the success of the program by providing reliable, stable, and accurate conductivity, temperature, and pressure sensors, as well as the Navis floats. However, there's been a paradigm shift in BGC measurements from ships to floats. If you look at the figure below of oxygen measurements over time, you can see that shipboard measurements have slowly been decreasing and float measurements have been increasing since about 2000 when the Argo program started. This indicates that initially ships were used for observational measurements. However, our floats are overtaking that, and now shipboard measurements are used for validation rather than observation measurements. And this shift was largely due to the success of the programs like Argo. So what is BGC? What is the BGC Argo program? Well, it was established to monitor the biogeochemical state or the health of the ocean over time. And currently there are 300 BGC Argo floats in the ocean. However, there's a plan to put over 1,000 of them in the ocean. And these floats will be outfitted with a variety of BGC sensors. Oxygen, nitrogen, pH, chlorophyll, suspended particle, and downwelling irradiance sensors are some of these sensors that will be on these floats. And SeaBird manufactures all of these. And the intent is to have the same success as they did with the original Argo program 2 decades ago. So why would you want to measure oxygen on a BGC Argo float? Well, oxygen is important for understanding the physical and biogeochemical processes in the ocean. For example, ocean ventilation and circulation, phytoplankton production and respiration, carbon export and sequestration, global ocean deoxygenation, and local oxygen minimum zones. It's also used as a critical variable in ocean BGC prediction algorithms, like the Canyon B pH prediction algorithm. Here at SeaBird, we use oxygen data to help us understand the stability of our pH sensors over time in the field when we can't actually take validation measurements. So I'll just show a brief example of how this works. You take your float data with oxygen, temperature, salinity, depth, and the GPS location. You put that into your Canyon B pH algorithms, and you predict pH across the depth in the ocean. You could then compare that to the profiles from the actual floats measurements taken, and then subtract the two to understand what the stability of that as compared to the algorithm over time. And the delta is shown up here in the far right at 1,500 meters. So why was an SPS 83 needed? First, we'll start out with why do you need an in-air calibratable SPS 63 in the first place? Well, optical oxygen sensors are stable in the water. However, they drift in storage before deployment, sometimes as much as 5%. And it's difficult to calibrate these sensors in the field prior to deployment. So what is the in-air calibration method? Well, optical oxygen sensors sense PO2, or the partial pressure of oxygen, and not concentration. You can use this partial pressure of oxygen to measure a reference measurement for an oxygen sensor any time in the air. So anytime the float surfaces, you can take a reference measurement. So how is this done? So a float coming up from the depths to the surface, remember from the last slide, and when it gets to 1 dbar, the pump turns off and it takes several measurements of temperature, pressure, and oxygen before it emerges from the water, where it takes several other measurements in the air. And these are used as your reference measurement that you can then use to calibrate your sensor anytime the float surfaces. So our current 63 is unfortunately not exposed to the air. It's actually integrated in the CTD flow path. So we needed to design a new sensor, which is the SBS 83. Essentially what we did was we took the 63 out of the flow loop, we flipped it 90 degrees and put it on the mast of the float, which now exposes the face of the sensor to air every time it emerges from the water. If you look in the lower right-hand corner, you can see how water flows through the flow loop, down through the CTD, then over the sensor, and then out the plenum. The plenum is specially designed to allow water to drain from it very efficiently. So now I'd like to talk about the performance of the 83. The very first float that we deployed was float 60 off the coast of Hawaii. And we've had almost a year's worth of data now. So at the beginning, before we applied the in-air calibration, we saw an error of about 0.7%. After in-air calibration or gain correction to the data, we're able to see a correction and an error of less than 0.001%. This was really good for us. There's also a concern about seawater contamination with this type of sensor. And seawater contamination is caused by poor draining or flushing of the plenum, seawater splash or spray, and rapid dunking of the sensor, which reduces the accuracy of the in-air cal. If you look in the right-hand corner, you'll see the diagonal line is an indication of measurements taken in the water versus the horizontal line, which are measurements taken in the air. And the red line that you see there is the least square of all of the data taken on float 60. And if you compare the in-air measurements to the red line, you can see that it's very close to almost taking all of its measurements in air, which means that there's very little seawater contamination with this particular float. We also deployed 3 triplet floats to assess the performance. And these floats were deployed to understand how the SBS 83 compared to the state-of-the-art, which was the Optode and the SBS 63. We deployed these 3 floats at Hawaii, the California Currents, and Station Papa. And we compared the surface O2 saturation between the sensors, and we saw very good agreement between all 3 of the floats. The surface O2 saturation difference between these floats was less than 0.5%, and the goal was 1%. So we were really proud of this result. If you look at the right panel, you see the results from the California Currents. And the top right figure shows the 83 data in red, the Andera in blue, and the Winklers in black. And if you compare the Winklers to the 83 and the Andera, we get high accuracy between the bottle samples at the deployment site. And this was a good news to us as well. Then finally, we did an analysis of the response time of the sensor. And you can see when comparing the response time of the 83 to the 63, it's faster than the Optode. And we can tell this by there's about double the arrow in the Optode to the 83 in the OxyCline on this particular flow. So in conclusion, the SBS 83 is an in-air calibratable oxygen sensor able to obtain accuracies of less than 2%. We assessed this on 6 alpha float deployments. It's also integrated into the CTD exhaust path, and the plenum was specially designed to improve the response time and in-air calibrations. And overall, we consider this project a success. And we plan to launch this later this year. Over to the right, you can see that we have some acknowledgments and some press from some of our collaborators at NOAA and the Tropical Pacific Observing Systems, which we're always happy to see. And we'd also like to thank the NOT program for their funding, and also our many collaborators at UW, MBARI, Scripps, and Hui. And now we're going to show you some of the people who took a part in designing and building of the SBS 83 here at Seabird. Thank you.
Hi, my name Hoa. I am title Technician Assembly in Calibration Group, and I have been work in Seabird about 15 years. I build product for SP43. It took me about a year to become confident in the build in the process. External component did not meet our standard. We have to bring component products in-house.
So after our sensors go through calibration, we analyze the data with our internal software to create the calibration fit equation. And at that point, then we can review whether the calibration residuals fall within the expected range. And if that's good, then it'll typically go on to the second calibration. And then if the repeatability within those calibrations meets our expectation for the sensor, then we consider it to be a good sensor.
I'm Daryl Carlson, Principal Mechanical Engineer at Seabird Scientific. So one of the biggest design challenges of the Seabird 83 development project was translating 63 performance into what will be the form factor of the 83. In-air calibration for optical oxygen sensors is especially important because Argo floats aren't able to be recovered. So that gives them the capability to recalibrate and reset the oxygen measurement to atmospheric conditions over the lifetime of the float.
All right, thanks, Nicole. I believe that's the end of the presentation, the video. Happy to answer any questions. I'll act as a moderator in the question and answer, or if I'm not sure if you can come off mute to ask questions. I'm not the expert at Zoom. I apologize.
Attendees can actually go ahead and type their questions in the Q&A in the chat box.
Thanks, Nicole.
Mm-hmm.
Nicole, there was one question that came up. We will be sending a link to the video. Is that correct? Afterwards?
Yes, the video will be going up, I believe, on our YouTube channel. It won't be available immediately after this, but it should be uploaded within the next week, I believe. Okay,
great. So we do have one question. Is the new 83 designed solely for float deployment? So Charlie, you want to speak to that?
Yeah, sure. I'm happy to talk to that. Yeah, so the 83 was specifically designed for just for floats, and that's because of the way that it's integrated in with the CTD duct and the new plenum design that we use to shed water off of it. So yeah, for right now, that's what it's used for, or that's what it's designed for.
Okay, great. And a follow-up question is, have we done any comparisons against other optos like the Renko 3 or the JRE Advantech?
So we only compared to the Andera and to the 63 as part of the NOP project that we were with Imbari and UW. And there are some other opportunities to investigate comparisons to other types of sensors as well, but we have not pursued those as of yet.
And I'll ask a question. As far as the performance against those, how did we do?
We did really, really well. The 83 is as good and in some cases better than the state of the art. So we're really happy with its performance so far. And we've deployed these on probably half a dozen different floats, 3 triplet floats, and probably somewhere between 6 and 10 other types of floats, being Apex and the new Solo from MRV, and also Navis floats. And we've seen comparable performances that I presented today.
Awesome. And next question, for shipboard profiling, is the SB43 still recommended over optodes?
Yeah, I think it's still recommended for those applications because you're looking for a really fast response time on shipboard profiling, and the response time of optical sensors is still limited in those cases.
And what is the plumbing distance between the the SB3/4C and the SB83? So do you know that answer? We might have to come back.
Yeah, I don't think I know that exact answer. I apologize.
Yeah, I don't know the answer to that. I apologize. After a year of measurements, has any biofouling occurred on the sensor?
So it's really hard to tell on a float, but we have seen a small amount of drift on the sensor over its year's deployment, which you could maybe say there was a little bit of biofouling there. And also at the very beginning of Float 60's deployment, we were doing daily profiles both at night and during the day. And we did see I would say, a relevant change in the response, both during the day and over those one-day cycles that we attributed to biofouling. However, once we went back to the 10-day cycles and we're only taking measurements or in-air calibrations at night, that seemed to go away. So yeah, I think biofouling does occur, but it really has to do a lot with how you're sampling the float.
What is the general recommendation or recommended anti-fouling technique for the optodes?
So right now, the recommended anti-foulant that we have is the anti-foulant cartridges that we supply for both our CTD products and for our float products, and that's the TBTO.
This is a good question. Do you know what causes the sensor to drift in storage?
So there's a lot of hypothesis, and there's been I shouldn't say a few different tries or attempts to understand this better. But right now we don't have, I would say, a real good answer for what exactly it is. Our suspicion is that it is a conditioning either due to pressure or hydration or possibly aging of the sensor over time. So, you know, desolvating of the membrane over time that causes the drift. But most of the drift you observe during storage, so not while it's deployed in the water. So once it's in the water, it's really pretty stable. So definitely some more work needs to be done in that to understand this better. But you know, there are methods and algorithms that can be used to correct it.
All right. Well, no more questions are coming in. Again, if you have any additional questions, please respond to the post presentation email. But we'd like to thank you for your time today, and we're really excited about the progress we've made with oxygen. And Charlie, do you have anything else to add?
No, I think I'd just like to reiterate, thank you everyone for your time. And I really appreciate the opportunity to give you, you know, kind of an inside look and an update on the new SBS 83.